And as I said, guys, I'm recording the lecture. Whenever we have the lectures, it's recorded, and you can find it on the video lectures and the slides on the lecture slides. Okay, now let's get started, and it's going to be the first official lessons that we have on Monday. Okay, now. Okay, before we start, I'm just going to give a kind of a bigger overview of the things that we want to do. And it's going to be about the concepts that we call that polynomials. In some textbooks like the McGraw-Hill, they start by the concepts of the polynomials, then they just move on to quadratic functions. Now we just start with the polynomial functions. Okay, what do we mean by a polynomial function? Okay, guys, so far, I assume that in Functions 11 course, that you have seen two things. You have seen that when we talk about the function, essentially is something like this. We say that, okay, the just starts, for example, with the two representation. And we have, for example, I should say a couple of, inputs in the domain. And we have some couple of outputs in the range of a function. What does it mean? It means that, for example, right now here, I'm just going to find a transformation. For example, imagine that this is the circle which I have here, which it contains 5, I should say, different elements. We call them the elements which they are in a set. That set defines, I should say, the domain of these functions. I call this one the domain. Imagine that each individual, I should say, elements of our domain, imagine this one. It is going to be transformed and changed. For example, by transformation, I mean that, for example, you have some raw materials. For example, you have pork, you have the powders, you have salts, you have peppers, and you want to make a dumpling. Imagine that the one which you have here is going to be the dumpling which you want. And the thing that we do here is that we say that the function is a way that to make this transformation from the pork, we just end up to have a dumpling. And that's what we call that. We call that the function, but instead we just call that the functions of the element that we had to make this transformation for us. This is essentially a kind of a very basic representation of what do we mean by function. And you will see here in a plate that you have gathered all your dumplings. For example, you have half a kilograms or half a pound of a pork, and you make here 1, 2, 3, 4, 5, 6 dumplings. These 6 dumplings in the plate here, we call that plate the range. And the method that you used to make this transformation from the raw pork into a dumpling, this is called the function. And essentially, as you see, that's how we define a function. We define a function as a transformation that transforms the raw materials into, I should say, the dumplings. This is a very basic representation of what the function does. So far, you have seen this kind of form of this transformation. I'm going to go to the next page. So far, you have seen a variety of these types of the transformation. For example, you have seen these functions. For example, you have seen that if you represent, for example, the x as a single variable, then you can construct a function, a transformation, which only this transformation incorporates the x. That's why we call that a single variable function. You see that the single variable function can take any arbitrary point, any arbitrary form, but sometimes subject to some restrictions. For example, you have seen this function, square root of the x. When we talked about this function, we said that, okay, when we have a functions like this, because the x is inside under the roof of a squared symbol in a function, we know always that x has to be positive. Or that's what we call that. We call this the domain of the function. It becomes all the sets of all the x's as a single variable of our function that the x belongs to the R. However, x has to be either positive or be equal to 0. These are, I assume that these are the things that we have talked about that when we started to talk about a function. We defined a function as a transformation that for each individual elements in the domain of the function, it transforms it into, let's say, for example, a range, which in that case, for example, it's going to be, for example, the real numbers, which are going to be the positive. That you know that the output of the square root is always positive. For example, the square root of 4, which is plus 2. Square root of, let's say, for example, 141, it's plus 12. Then we talked about the range. Then we saw that the range also, it's going to be the values. We call that y belongs to the R real numbers. However, those y's also follows this definition. These were to talk about the range of the function. But for this function, you see that it had a completely different shape of the function. It was a squared function, square root function. Now, however, our new lesson for today starts right now. That one we talk about the polynomials. When we talk about the polynomials, what do we mean? We come here and say that polynomials, still there are functions. I'm going to write it here. Polynomials are type of a function or a transformation, but with a different characteristics. But what is that? I'm going to say, okay, I'm going to choose a single variable because we know that in functions 11, we always work with one single variable, and we call that single variable always x. I say that I'm just going to start by one single variable, it becomes x. And why do I call it variable? Because it can changes. X, right now, it can be, for example, 1. A couple of seconds later, you can choose x to be, let's say, minus 1000. It changes, and that's why you call it variable. I say, okay, for the x, which I have here, I'm going to transform it. That's why I plug it with a function. Then the f of x, here it means that the x is going to come here to transform whatever arguments it can find inside. However, I say, okay, this form is not going to be, for example, like the square root of the x. It should be in this format. I say that, for example, I say a sub-index, for example, n, x, it's going to be the same x here, but it goes to the power n, plus a, I'm just going to write index, sub-index x, n minus 1, I'm going to explain to you what do I mean by these a's in just a second. And that's the general format of the polynomials. Then I call that x to the power n minus 1 plus a and x n minus 2. Again, my single variable, which I call that x, still this is x, n minus 2. And this process goes on until we get to a 2 x to the power 2 plus a1 x to the power 1 plus a naught, we call that a0 or a naught nut x to the power 0. This one, the thing which I have framed for you here, it means this is essentially, that's what we talk about that as a polynomial. This is the general format of a thing that we call that polynomial. Okay, but I'm just going to spend the rest of the class to tell you which one is which and what is the significance of each element there. First of all, look at this. For a polynomial, you have, first of all, look at your variable. The variable which you have here is x, the same x which I had there. Still I have x, still I have x. I do not have x here, then I have z, or let's say w. All of them uniformly are represented by the x. However, you know that x to the power 0 becomes 1. I'm going to show that a little bit later. The first check which we do is it is still a single variable function. We just start by one single variable, which is x, and we keep the variable to be the same thing at each term. I do not have here x, but here I should have z or w or v. Every single value remains the same. That's going to be the first thing. The second thing, you see that I have an exponent to the x. n minus 1, n minus 2. I have 2 here, which is going to be our exponent of interest today. Then I have 1 as an exponent for single variable, and I have 0. X to the power 0 becomes how much, guys? Becomes 1, huh? Okay. And now this is so far the thing which we have. These are the exponents. And which exponent is the higher one, guys? It starts from n. For example, imagine n is going to be 4. Then we have 4, 3, 2, then the rest. And the last thing, which is important also, we have these ones. We have a of sub-index n. You see these elements, a, a1, and also a naught. These are, I should say, we call a, let me write it here. We call a, we call them coefficient. Coefficients of the polynomials, which you will see that in functions 12, advanced functions, they have very interesting interpretation. Now, I'm going to come here to show you something. We said that these coefficients, which are going to be the coefficients a, they all should belong to real numbers. For example, 2, minus 1000, minus the square root of 5, anything. And essentially that's the general format of, I should say, the polynomials. For example, as an example, I'm just going to show that to you as an example, f of x as a polynomial, I can just, for example, choose n equal to, let's say, 4, and I write, for example, 4 times x to the power, for example, 5 plus square root of 2 to x to the power 4 plus, let's say, for example, x to the power 2 plus 5. This is an example of a polynomial which in a polynomial we see that our single variable is x and it remains to be x. Then we have a single variable function. I should say, the power, the coefficients, look at that, the coefficients is 4, square root of 2, 1, and also 5. All the coefficients, they are real numbers. And I can see the exponents is gonna be 5, it's gonna be 4, it's gonna be 2. In this case, if this example, you see that the n, if n is the highest power of your single variable function, we call that, we take the n, which is the greatest one. We have 5, we have 4, we have 2, and we have 0. Essentially, it's going to be x to the power 0, which becomes 1. Then we see that n is going to be 5. And that's going to be the lesson that we learned today, that anytime that you are just going to work with these functions, then we see that we pick up the n, which is going to be the highest one, and we call that the degree of the polynomial. Then we are going to say that n, which is essentially the highest power of the polynomials, represents the degree of the polynomial. Okay, what do I mean by this? Okay. Guys, what is going to be the highest degree of the polynomial here? In this example, the highest power is 5. Huh? Then we call that the polynomial is degree 5. It's going to be polynomial of degree 5. However, guys, any questions so far?
No.
Everyone is fine?
Yeah, it's good.
Okay, nice. Okay, now, we also, when we talked about the polynomial degrees, which we have polynomial of, let's say, for example, degree 5 here, the coefficient of the highest power, which in our case is, the highest power is 5. The coefficients of the highest power of the single variable is how much? Is 4. Then we take 4, we call 4 as the leading coefficient. We call the coefficients of the highest power the leading coefficient. you will see that in just a couple of seconds that when we talk about, I should say, the plotting of these polynomials, these leading coefficients plays a significant role. You're just going to see that in just 1 second. And now also, we just go to, for the next example, I'm just going to say here, I'm just going to still talk about let's say, for example, when n should be equal to 3, for example. When n is equal going to be to 3, if I just want to construct a polynomials, if x is going to be equal to 3, then it's going to be very simple then. Then I say that, first of all, I come here to pick up a single variable. I'm going to call that single variable x. You can call it anything else if you want. The thing which is important is that that thing is just going to remain the same. For example, in order to see also something different, I'm just going to come and call my single variable as, let's say, for example, z. Or you can just pick up your single variable as, let's say, for example, w. Then you come here, you say that, okay, I'm just going to pick up a function which represents my single variable w, but I make sure that its power is going to be 3. Then you say that it can be as a very general format. It can be a3 x to the power 3 plus a2 x to the power 2 plus a1 x to the power 1 plus a0. You can just write either x to the power 0, or you cannot write it. Normally you do not write it because that's what you called it, the intercept. Look at this one. For this one, the first check is going to be correct. We have one single variable. We call that w. Oh, sorry, I just put x here. Just, it's my mistake. I kept writing the x because normally that's what's the convention. You write x for the variable, but the purpose was to show you that you can write the single variable any name you want. First of all, on our check, we see that we have one single variable initially designed as w, and we were faithful to that. We just kept that single variable all over the equation. We see, however, that the power, the highest power of our equation is going to be 3. That's what exactly matches with the thing which we expected. And a3, these ones essentially, they represent these coefficients of the function. You can pick up them anything that they should be real. You say that a3, a2, a1, and a0, all of them should belong to the real numbers. Then you can come here and say that, okay, I'm just going to pick up an example for myself. I say that, okay, I'm just going to assign a, for example, fw. For example, a3 becomes, for example, 2. You have w3 minus square root 2 of w to the power 2 plus, let's say, 10w plus, let's say, 7. That's an example of the polynomial of degree 3. That's polynomial of degree 3 because the highest power is 3 and the leading coefficient is 2, which is a positive number. Then when we just do the plotting in just a couple of sessions ahead, you will see that the leading coefficients, it's very crucial when you just want to do what they call that, the endpoint behavior of the function. Guys, any questions on this one?
No.
Polynomial degree 3. Okay. Now, what we want to do right now is essentially that's, let me go back again. Okay, with these functions, polynomial number degree 3, we call them also polynomial degree 3. We call them cubic functions. Now, we just come here and also talk about, let's say, for example, if the highest level of, I should say, polynomial is going to be number 2 and is going to be 2. Then what's going to happen here, the thing which is going to happen here is that we just come here to define, for example, a single variable, which we can call this anything. We can just call that single variable anything. I just call this one here, for example, z. I say that, okay, I'm going to find a function which represents z as a single variable. Then I say that it's going to be a2 as a coefficient of x2 plus a1 as a coefficient for x plus a naught. Okay, again, I put x. The purpose was that to show that we can change the variables to anything we want. Then I put that this one z here. You see that again, we have been faithful, I should say, to the variable. Everywhere we have z. And also you see the power of our variable polynomials, the highest power is 2. And the coefficients that we have, it's a2, a1, and a0. And each one has to belong to the real numbers. We call a0 as an intercept. When we do mathematical modeling, it has a very interesting interpretation. And we call a2 and a1 as slope. It has a highest degree of 2. That's what we call that the polynomials of degree 2 is called quadratic functions. That's what we call them, the quadratic functions. Okay. And now, and also here we see the leading, I should say the leading power. It's going to be the leading coefficient. This one is the leading, I should say, leading coefficient. As an example of the polynomials, you have seen this function, for example. As an example, you have seen, for example, f of x. It becomes x squared plus 2x plus pi, for example. That's going to be an example, which the leading coefficient is going to be 1 plus 1. Okay. Guys, any questions so far?
No.
Oh, okay. Now we just want to see some, I should say, the basic characteristics of these functions as a polynomials. But for the polynomials now, we just focus our attention just from now on for the rest of the book which you have. You are going to talk about the polynomials, I should say, of degree 2, which in a sense, you do not go to talk about, I should say, polynomials of the higher degrees, for example, degree 3 or degree 4 or something even higher. We focus for the rest of the book our attention to the polynomials of degree 2. And also, I'm just, if you are interested, I'm just teaching the other class which I have, because we have extra time, some mathematical codes into a programming which is called R, in order to make the inference and make predictive models as a part of artificial intelligence with the polynomials there. If you are interested, I can share those lectures on YouTube with you. You can just see that on your spare time. But nonetheless, we come here, we talk about, I should say, the plotting of these, I should say, variables, these functions of quadratic functions. We said that when you just want to talk about, I should say, for example, the polynomials, the other thing which I want to talk to you about that, it's the concept before I get too much into the details of that. It's going to be the concept of the endpoints of the endpoint behavior of the polynomials. Look, for example, the thing which I want to do is gonna be, I'm gonna plot the polynomials as an example for you. Which I show half of it. I call that f of x is half of this polynomial. Let me do that from the other side. It's going to be much easier to explain that to you. Okay, that's going to be my f of x, which is half of the polynomial, which I wanted to show that to you. Okay, now look at this one, guys. When you, for example, when you are walking from, let's say, imagine that you are walking, imagine that this is going to be, for example, it's going to be, let's say, for example, Tom. Tom is walking, let's say, for example, along the x-axis, and he is walking along the x-axis, going all the way, getting close to the origin of this plot. As he's walking towards, I should say, the positive, I should say, of the x, Tom is going to measure the value of the functions. When he is here, he's going to look above his head and to see what is the value of the function. He's going to look up there to see that at which point his eyesight is going to cut the plot to find the value on the y-axis. When he is reaching here, for example, when Tom is here, getting close to here, let me show that to you by a single line. This part is not going to be a part of the plot. That's something which it shows that to you then. It shows to you that the function which I'm plotting when Tom is getting close to the function, there is a point that, for example, let's call that point, for example, 5. When Tom is getting close to the point 5, he sees that the function is going all the way up there. And the value of -5, although the value of the function, it goes all the way up. That he cannot essentially see where the function is going to be presented, let's say along the y-axis. It goes all the way up there. Or where, for example, wherever he's here, contrary to the thing which he saw that, for example, he look up there and he sees, for example, the point at the function. He can find, for example, at this corresponding point, for example, which I call that x0, he finds, for example, the f of x0 here. At this point, which I have an asymptotic line for this, that's what I call this, I should say the endpoint behavior, that the function goes all the way up there when you just go, for example, you go x to the minus infinity. For example, if Tom is moving from backwards, going to the minus infinity, it means that it becomes, for example, from minus 20 to becomes 1 minus 1,000 to minus 100. Have you seen this symbol before? Guys, have you seen this before?
Yes.
Okay. Then when you Tom, for example, changing the direction, going all the way from up there to the minus infinity, he sees that the function goes all the way up there. For example, you just go to the CN tower, when you're standing next to the tower, you just look up. You see that it seems that the wall of the CN tower, it just goes all the way up there. And that's what we talk about the endpoint behavior of the polynomials function. But in order to understand, I should say, some aspects of it, we come here on the next slide before we just go to some plotting and finish the day for it today. We just talk about in our function as it was, let's say, a2x squared plus a1x plus a naught. I told you about the fact that we say that the a2 is going to be our leading coefficient. Then as a result, I'm just going to talk in two different scenarios. Scenario one is a case that a2 is going to be a positive number. And also we have our another scenario today that the leading coefficient a2 is a negative number. We're going to talk about these two things briefly, then we finish the session today. Tomorrow when we come back, we do some more analytical stuff of these quadratic functions. Now we are just going to get to know them from a bigger family, which are polynomials, and reduce the order going to the second order, which is called the quadratic functions. At this stage, we are there. We say that if the leading coefficient, which is a2, is positive, how the function may look like. In order to show that to you, I'm gonna, I should say, go to a graphic calculators and show there to you what's gonna happen there. Guys, so far what, in terms of the graphical calculators, what have you been using before?
And using in homework.
You're using what?
When we are doing homework.
Okay, you didn't use any graphical calculators, huh?
Yeah.
Okay. Let me stop the share. Guys, please listen very carefully to this part because if you haven't used that before, I'm gonna show you how to use a graphical calculators, which is essential for the rest of the term with me. Look at this. I'm gonna share my screen and I'm taking you to my Internet Explorer, which I use, I should say, the Google Chrome there. In order to get there, I'm just going to do that again. You have to write Desmos. Let me just go to the Google. Anybody use Desmos before?
I know it.
Okay. I'm just going to search for Desmos graphing calculator. And the option which I take, it's going to be this one, graphing calculator with the Desmos. Okay. Now, in our first scenario, we can just plot any function that we want. For example, as a very easy example, I'm just gonna plot a function which is gonna be what? Which is gonna be, let's say, a quadratic function, but I bear in mind that its leading coefficient has to be positive. As an example, I can just plot this function. I can plot 4x, and I'm pressing shift number 6, which it takes it as an exponent. I know that the power, it should be 2 because I'm working with the quadratic function. Plus, let's say, for example, 2x minus, let's say, 5, for example. You see this function which is plotted. This point, which is going to be point minus 0.25, and this we call it turning point. We're going to talk about that tomorrow, what does it mean. But I'm going to plot another function with a different color. I call that y equals to, for example, x squared plus, let's say, minus 3. I'm going to plot another function, but with the positive leading, I should say, coefficient. I call that x to the power 2 plus sqrt, which is the square root of, let's say, 3x. It's another polynomial function, a quadratic function. However, as a very last function, I'm just going to y equal to, let's say, for example, pi x squared, because you know that the pi is a number itself, minus 2 times x. I think that's going to be fine then. Okay. We have 5 minutes only, then let's catch up with the things, the conclusions that I want to drive right now with you. Guys, look at that. All these functions which I have, which is function which is plotted in red, the function which is plotted in blue, green, or purple, you see the common things which they have. First of all, is that all of them, they are quadratic functions, or they are polynomial functions of degree 2. It's 2, it's 2, it's 2, it's 2. That's the first thing which all of these 4 functions share, and they have in common. The other thing which they share is that all of them, the leading coefficients which they have, the leading coefficients was the coefficient of the highest power of the single variable. In our polynomial degree 2 or quadratic functions, you saw that the leading coefficients is the coefficients of the x to the power 2. For all of them, which is 4 plus 1 plus 1 and pi, all of them, they are positive coefficients, positive real number as a coefficients. For all of them, if that's the thing which they all share in common, you see that all these functions, they are in a way that when you walk from the x from minus infinity to go to the plus infinity, you initially saw that as the x is increasing, the function decreases to a point that it's going to be the lowest point, for example, here. Then as you move along, the function starts to grow, to increase. That's what we call a turning point. We're going to talk about that tomorrow, how to drive it. But the thing which we just want to wrap today is that all these functions are in a way that they are occupying the quadratic one of the Cartesian coordinates and quadrant number 2 of the Cartesian coordinates. Anywhere which they start as an intercept, even from -5 here, they always pointing upwards. It becomes like the glass that you want to, for example, do what? You feel it, you feel the jar with it then. You see, it's like you can feel the glass. It's a glass of the water, the blue one, the red graph. You can feel this with the water to come up. We talk about this one sometimes in future, convexity or concavity, but not at this stage. So far, look at this plot, look at this graph. Now, another thing which I want to do, you remember with the second scenarios that we had, it was the first scenario, that the leading coefficient is something positive. Then if that's the positive, like this one, it acts like the jar of the water. You can feel the water at the bottom of this plot. The second criteria was this, and I finished this in 1 minute, then we can leave them. The second criteria is this: if the leading coefficients be a minus number. Look at this. When I plot it, the function is exactly upside down. When I plot it, this function also, the function is upside down. Look at this plot. The green one. The green one is a positive, it has a positive coefficient. If I took it to -1, you see the plot is turned back down then. And also for the last plot, which is the purple one, if the leading coefficients, it's changed from plus to minus, you see that the function, the jar of the water you have, is just upside down, and you turn it back. And that's the characteristics of all these, I should say, functions that we have. Does it make sense to everyone? Then in order to finish it, I said that if the leading coefficient is positive, we get the plot something like that. However, if the leading coefficient is negative, we get the plot something like that. Okay, I think that's going to be all for today. Today's session was very quick because we had to start the first session for introduction of the course. You're gonna see the lectures that we had today. I'm gonna create 2 folders, video lectures and the slides. I'm gonna post it there. If you have no questions, then I will see you tomorrow then.
Okay.
Thanks everyone, and see you all tomorrow, and have a nice day. Take care.
Thank you, sir. See you.
Bye everyone, see you tomorrow.
Yeah.
Take care everyone, bye-bye. Bye Jesse.